bunch more examples. So. So here, let's go back. So if you remember, I had this example from last time of these cluster states. So the cluster state being when you have a graph, you put a qubit on it, on every vertex of the graph, and you have a stabilizer that's x on the qubit, and then z on the neighbors of that qubit. So this guy's stabilizer is x, z, x1, z2, z3, like that. This guy is x2, z1, z4, that, and so on. And that works for any graph. It defines a perfectly valid stabilizer state. That's called a cluster state or a graph state. So let's see. All right, so first of all, let's talk about preparing cluster states. Let's talk about reducing, I don't know, reducing them. Let's talk about computing with them. Right, so first of all, preparing a cluster state. So for preparing a cluster state or a graph state, we know the following rule. When you have a C0, it copies X forward, it copies, it leaves Z on the control qubit alone, it conjugates, I don't know, it conjugates an X on the second qubit into an X on the second qubit, and it conjugates a Z on the second qubit, it copies it backward. I don't like this notation. Let's do it this way. Let's keep the same equations I had here. X is equal to X so that's how C0s work. If I have a controlled Z gate, so a controlled Z gate, remember the notation was this. It's funny notation for a controlled Z gate, which is equal to the 4x4 matrix, like that. So this is equal to a controlled NOT gate conjugated by Hadamard's, because the Hadamard's change the X into a Z, or it's also equal to a controlled NOT gate conjugated by Hadamard's. So this controlled Z gate, if you think about what happens, if I start with an X on the first qubit, that's the same as it's conjugated by the controlled Z gate. So the controlled Z gate, it squares to the identity, just like control NOT. So I can just write the conjugation like this. X, right, so the C, if I had a C0 gate, this X would become XX. But actually I have an X here, it's becoming XX, and then the Hadamard's changing into a Z. Yeah.
So how can we distinguish the target qubit from the control qubit?
There is no difference between them. Right? I mean, the matrix is 1, 1, 1, minus 1. So it's totally symmetric when you switch the two qubits. Yeah, that's why both of these are true simultaneously. Yeah. Right, so here, this X, it's copied into an X here, which is switched into a Z there by the Hadamard. And so an X on the control qubit is sent to that, and that's true with either control qubit. So an X on the second control qubit is also conjugated to XZ. And a Z on either qubit will commute, right? So a Z on the first qubit will commute all the way through, a Z on the second qubit will commute all the way through. So I can write that down, sure. So in other words, if I want to apply a graph state, what I can do is, say I want to prepare this is psi g, psi of g, g, I don't know. The graph state corresponding to this graph. I just, let's give them numbers, I don't know, 1, 2, 3, 4. And so the circuit I want to apply, I should start with ket plus on everything. And so right now, here, the stabilizers are x, I, x, I, yeah, and x4. And so now I'll just do controlled z gates along every edge. So from 1 to 2, what happens with that controlled z gate? This will become xz, and that'll become xz, zx. Alright, so controlled z gate from 1 to 2, I have xz, I, zx, I. The other two are unchanged so far. Now let's do controlled z, I don't know, from 2 to 3. Controlled z from 2 to 3. Alright, so this one's going to be changed. It'll become iz, xi. This is left unchanged. But also this one here, the x will be copied forward into a z. From 2 to 3. Okay. So now let's do, I don't know, 3 to 4. Alright, so first stabilizer is unchanged. Second stabilizer is unchanged. It commutes. Alright, so these ones are changed. So IZX is going to be copied forward. Here, let's IZX, Z, that's changed. And this one here is copied backward. Like that. Go to 3, 4. And finally, that's this gate here. Finally, let's do controlled Z gate from 1 to 4. Controlled Z from 1 to 4. And so copy, paste. Alright, so x1 is going to be copied into z4. That commutes. X4 is copied into z1. Like so. And this now is exactly what we want. Right? So x1, 2, and 4. 1 next to 2 and 4. The second stabilizer is x2 times 1 and 3. Third stabilizer is x3 times 2 and 4. Fourth stabilizer is x4 times 1 and 3. Yeah. So I've generated this graph state using 4 different controlled z gates. And actually, maybe it would be better. Like I could have done it. So controlled z gates commute with other controlled z gates because they're all diagonal. So diagonal matrices all commute with each other. So maybe it would have been better to do like this blue gate and this red gate at the same time. You could do them in parallel because they're in different qubits. So 1 and 2 and 3 and 3 and 4 at the same time. Then you could do 2 and 3 and 1 to 4 at the same time in parallel because they're acting on totally different qubits. So you could do it in 2 rounds, each round involving 2 gates. And the same thing works in general, or with a general graph. To prepare a general cluster state or graph state, you just you start with the all plus state, so stabilized by the x operators, and then you apply controlled z gates on all the edges. any in any order because controlled Z gets commute. That'll give you exactly what you want. It'll have an X on every qubit and a Z on all of its neighbors.
So,
Yeah.
so is that the general rule applying the implementation, applying the CZ along the edges?
That works for any graph state, yeah. Yeah. And so you can see that like the number of rounds you need. Is it like the degree of the maximum degree of any vertex? Maybe. So if you're trying to parallelize it, so to do as many control Z gates in as few steps as possible, it's probably just like the maximum degree. So here's another example. Let's do a couple more examples. So I use this notation.